Sorry about stopping halfway through that last example, guys. I'm using QuickTime to record these, and QuickTime just notified me that I was done. So we'll go ahead and start part 3, which is more examples of trig derivatives, and we'll just go ahead and pick up where we left off. We weren't that far into this problem anyway. What we have right here is we were given a function, y is equal to sine t over 1 plus cosine t, and we wanted to get the equation of the tangent line at t is equal to pi over 3. Okay, well, at that point we need to go ahead and plug it in. Okay, and we're going to go ahead and plug it into the function in order to get the rest of the ordered pair. And the rest of the ordered pair winds up being root 3 over 3, largely because we have sine over 1 plus cosine. So when we evaluate, we get sine pi over 3 over 1 plus cosine pi over 3. Well, sine of pi over 3 is root 3 over 2. Cosine of pi over 3 is 1/2. And, you know, when you go ahead and add up that denominator, you get root 3 over 2 and 3 over 2. If we were to go ahead and divide or multiply by the reciprocal, get root 3 over 3. And that winds up being our point. Now we need the slope. Well, here's why I chose this problem. This is one of those ones where if you really know your trig IDs, this winds up being very, very easy. We're going to go and do it the long way, and then I'm going to show you the trig ID, and that'll give us the short way. Okay, so let's go ahead and put y prime, and we have the bottom times the derivative of the top. Okay, I almost put an x there, then I remembered it was t, times the top, sine t, times the derivative of the bottom, which winds up being negative sine t, right? All of that over 1 plus cosine t squared. So we get cosine t plus cosine squared t plus sine squared t, all of that over 1 plus cosine t squared. Okay, so that right there is a Pythagorean ID, and I'm going to go ahead and flip the order around to make it a little bit more apparent that that is going to simplify into 1 plus cosine t. Okay, so now I can actually evaluate the derivative at that same t value and get 1 over 1 plus 1/2, or 1 over 3/2, or 2/3. So in terms of point and slope, I now have both. I have point and slope. Okay? And so all I have to do is y minus root 3 over 3 is equal to 2/3 times x minus pi over 3, and that can be my point slope, right? Now, I told you that there was an easier way to do this, and there is, okay? Some of you should have recognized that form right there because it was one of those IDs that became so popular in a lot of the worksheets that we did. Sine over 1 plus cosine is equal to 1 minus cosine over sine. Now, if you don't believe me, just multiply this one by the conjugate of the denominator. Okay? And you're going to get the 1 minus cosine squared on the bottom, which of course by Pythagorean turns into sine squared, one of which cancels with that numerator, and voila, we have that. Well, the thing that is so nice about this is that it simplifies because it has a monomial denominator. And if we take that monomial denominator, then y prime winds up being negative cosecant cotangent plus cosecant squared, sorry, it's supposed to be a t, and then if I want to go ahead and factor out a little bit, it's supposed to be another t right there, cosine or cotangent t, we get that. Okay? Well, you know, evaluating these at pi over 3 may not be the best thing in the world, but at least you don't have to use the quotient rule, right? So you actually can evaluate these, and if I go ahead and evaluate y at pi over 3, I'm going to go ahead and get cosecant t minus cotangent t, or sorry, it's supposed to be cosecant pi over 3 minus cotangent of pi over 3. Okay. Well, what's sine of pi over 3? Well, sine of pi over 3 we've already determined is root 3 over 2. Okay, so this is 2 over root 3. Now, cotangent of pi over 3 is going to be what? Well, cotangent of pi over 3 is obviously going to be is the reciprocal of tangent of pi over 3, and tangent of pi over 3 is root 3. Okay, so this is 1 over root 3. Well, the reason I go ahead and leave it right like that is because this winds up being 1 over root 3, which of course rationalizes into root 3 over 3, which is exactly what I got for the function output when it was in the other form. If I have y prime of pi over 3, that's going to be cosecant of pi over 3 times cosecant of pi over 3 minus cotangent of pi over 3. And of course, cosecant of pi over 3, as we've already talked about, is 2 over root 3. Okay, and this, of course, right here is what? It's the same as this, right? Which is 1 over root 3, so that winds up being 2/3. And if you recognize, those are exactly the values that I got up there. It just depends on whether you want to avoid the quotient rule, which for some people is a pretty big incentive. But in terms of evaluation and in terms of the equivalence of these forms with respect to these forms, this is just another way of doing it. And if you like it, do it. If you don't, because cosecant and cotangent give you the heebie-jeebies, then by all means, just skip it, okay? Now let's go ahead and, now that we finally got that one under our belt, let's go ahead and move on and do a couple more examples from a couple more worksheets that I pulled off. Let's say we have y is equal to 3, 1 minus sine x, all of that over 2 cosine x, and I want the derivative of that. Well, that looks kind of nasty, but it needn't be, okay? Because remember that if I can rethink this as that, and just think of 3/2 as the coefficient, then I can also rethink this as that. And it winds up going term by term, and I don't have to use the quotient rule. Because, you know, if you don't have to use the quotient rule, why in the world would you want to, right? So let's go ahead and do y prime. And you wind up getting 3/2, and we'll just go ahead and go term by term inside here. The derivative of secant is secant tangent, and the derivative of tangent is secant squared, okay? And that winds up being nice and neat. And actually, I would just go ahead and just leave it like that. I mean, unless you're asked to do something with it that requires you to change the form, there's no need to change the form just willy-nilly. All right, let's go ahead and do one that, you know, not really nasty in terms of being all that difficult, just one of those burdensome ones where you just kind of, where I used to hear y'all sigh deeply as you came to it on the tests, okay? Now, can we change the form of this? Sure, I don't think it's going to really be advantageous at all, because it doesn't really get rid of the problem, and the problem is that it's 2 terms and both terms require the product rule. I think it's just easier just to go ahead and grind it out. So let's go ahead and do that. we'll go ahead and we'll deal with this first one first, okay? So let's go ahead and put some braces up there so we can sort of distinguish, so that when, if we were to come back to this problem, we want our notation to be nice and clean so that we don't have any question as to what we did. We know exactly what we've done because we've kept it all nice and tidy and stuff like that, okay? So we have the first times the derivative of the second plus the derivative of the first, and of course by first I'm actually lumping the 2 in with the x. I'm not bringing the 2 along as a coefficient. And you can do whichever way you want. I just chose to do that just to make it a little bit easier on myself. And that is the derivative of this first one right here. Now let's go ahead and do the derivative of the second one. We'll go ahead and take the x squared and then the derivative of cosine plus the derivative of x squared times cosine. Okay? And what we have here is obvious, well, not obvious, they're pretty far apart, so it may take a second, but that is like terms with that. In fact, they're identical terms. So if you have 2 x cosine x over here and 2 x cosine x over here, then together you have 4 x cosine x. We'll go ahead and put 2 sine x, and then we'll go ahead and put the negative term last. It doesn't really matter. But that right there is the derivative of that particular function. And only nasty, just not nasty, just burdensome, because it went from 2 terms to 4 terms and required a little bit of cleaning up. So it wasn't really all that straightforward. Now, let's see. Okay, let's go ahead and just do a few more. And then we'll sort of call it quits. And then I'll sort of wait for you to prompt me if you need any more practice on trig derivatives. Now, trig derivatives will come back in the chain rule videos that will also be coming down the pike. So, you're going to get your fair dose of trig, so you may not need any more than what we're doing right here. Let's go ahead and back up and do one that's actually relatively simple, just to make sure that we actually get through all of these. Okay, say I have sine cotangent x. Now, this one, you go, oh my gosh, it's the product rule. It's not the product rule. And I'm going to give you a second so that you can try and figure out why it's not the product rule. I want you to stop. I want you to think before you do. Because this, my friends, is just cosine x, which gives me y prime negative sine x. Cotangent has an implied denominator of sine, which cancels with this sign, leaving only the numerator in terms of it being simplified. Okay, well, let's go ahead and instead of doing that one, let's do one that's perhaps a little bit more difficult, which is sine x tangent x. And y prime for sine x tangent x should be really straightforward. This one actually is the product rule. I mean, you could transform this into sine squared x over cosine x. But that seems more like a step backwards than a step forwards, unless, of course, you then turn this into 1 minus cosine squared over cosine, which then becomes secant x minus cosine x. And I guess you could do that. It's a couple of steps away. But, if you see it, then do it. Because certainly this is term by term, whereas this is not. So we have first times the derivative of the second, okay, plus the derivative of the first times the second. Got it? And of course, this winds up being sine x secant squared x plus sine x. Right. Okay, well, let's say we went ahead and did it with this one over here, and this winds up being, well, secant becomes secant x tangent x minus, well, it becomes plus sine x, And of course, you're like, well, that is different from that. It really isn't. Because in order to go from here to here, all you have to do is take the cosine that is implied in the denominator by tangent and allow it to be absorbed with the secant x to become secant squared. And all that's left over after you allow that secant to be absorbed into this secant is the numerator of tangent, which is of course sine. Those are equivalent derivatives. But of course, I think in this one, you spend more time changing the form, and there's just as many places you can go wrong here in changing of the form in terms of careless errors as you can here in terms of a very straightforward, very straightforward product rule problem. Okay. Thankfully, QuickTime did not cut me off this time. I think that brings us to the end. I don't think we really need to do any more. Like I said, the trig derivatives will be folded in 3.4 with all the chain rule stuff. We may revisit some of these examples, especially the double angle identity one that I did in the last video, because the chain rule certainly applies there. But I hope that this was helpful, guys. Shoot me emails, leave me comments, whatever, if you need anything else in terms of trig derivatives. See ya.